mineral assemblages occur at different temperatures throughout the history of the deposit. Briefly on deposit type that is somehow related but not the same as porphyry. This is GREISEN deposits, and instead of forming from I-type granitic magma, they are related to S-type granitic magmas, which are those granites that are derived from partial melting of sediments. And they are generally fluorine and boron rich. So these are often sources of tin and tungsten mineralization, which occurs as oxide minerals. Tin we're seeing cassiterite in the lab last week. Main oxide of tungsten is scheelite, which is calcium tungsten oxide, which we didn't see last week. But nonetheless, these oxide mineralization occurs inside veins in the granite or just outside of it in the country rock. And as we move further away, the chemistry of the fluid changes, and reactions with country rock cause the precipitation of copper, lead, and zinc sulfides. And these we will see tomorrow. And this GREISEN type of deposits it's got its own kind of alteration characteristics, especially close or within the intrusion itself, with these topaz and tourmaline and fluorite, which are characteristic of it. Another deposit type, which is somehow related, is SKARNs. These don't necessarily depend on the magma that feeds into the system and provides fluid, but they need basically carbonates in the country rock to occur. So we have basically metasomatic replacement of carbonate rocks following the intrusion of magmas. And they can occur associated to porphyry deposits. So if we start with, for instance, a Bingham Canyon, porphyry systems that shallower up encounters some carbonate in country rock, we can cause these reactions that precipitate minerals in different ways. And these SKARN deposits are related, as I mentioned, not necessarily to the deposit, to the magma type, but different magma types then come related to different ore deposit types. As you can see, I-type granites tend to be associated with copper and zinc and gold, whereas S-type granites tend to be associated with tin and molybdenum. And this is just an image of carbonate beds that have been reacted with fluids and formed sphalerite and scheelite, or pyrrhotite and scheelite. As SKARN deposits are formed, basically we have 3 stages of formation as we inject magma in a system where carbonates are present. We start to metamorphose these carbonates. We form basically marble through heating of the system or rock. We dehydrate the carbonates, which forms porosity and allows fluid flow and may form some initial mineralization. In a second stage, we have metasomatism and replacement of the country rock. We've got boiling, so separation of fluids and magma, and fluids that migrate and react and replace the carbonates to form these so-called exoskarn, which forms outside of the intrusion, or some sulfide precipitation might form endoskarns within the intrusion. And that's when we form magnetites and shear lines. Later on, in a third stage, we've got retrograde metamorphism of the marble. We get disseminated mineralization due to the influx of meteoric waters. And we have precipitation of other sulfide minerals, pyrite, chalcopyrite, or magnetites proximally, or spirite and galena more distantly from the deposits. On to the last deposit type for today, epithermal. And you know what these are? This is White Island, and that's another geothermal system. Tarpon, Rotorua, Hauraki, Korako. Anyway, epithermal deposits are, as it says, related to large-scale convection of groundwater and magmatic waters, and they are related to recent volcanic activity. Here we have an increasing effect of non-magmatic fluids, especially in one of these two types. So we've got high sulfidation, which is say proximal to the magmatic intrusion or the volcanic system, and the low sulfidation, which is more distal, where meteoric fluids have a greater influence. And this is just a schematic diagram to illustrate how epithermal system relates to porphyry systems. So we have a volcanic system, an intrusion of depth, where the fluids dissolve from the magma. We might have these proximal systems that form porphyry vein and disseminated pores. And as these fluids migrate further towards the surface, if they are within the volcanic system, we form high sulfidation deposits, and if these fluids migrate away, they can interact to a greater extent with meteoric water, which basically neutralizes the acid character of these fluids, and they form low sulfidation deposits associated with hot springs. And of course, there is a spectrum between these two members. Nothing in nature is black and white. So for instance, we have high sulfidation on the left, low sulfidation on the right. In one system, the fluids tend to be oxidizing, and in the other system, reduced or reducing. As I said, in high sulfidation, the fluids do not interact to a large extent with meteoric water, and so they retain the acid character and high salinity, whereas in low sulfidation, we have fluids that interact with meteoric water, so the pH is neutralized and the salinity reduces due to mixing. Different deposits are related to different alteration assemblages and metal associations, whereas high sulfidations we might look for gold and copper. In low sulfidation system we might find more silver, gold. And again, close to a volcanic system we have high sulfidation deposits, and further away in geothermal areas and hot springs we have low sulfidation systems. The precipitation processes for high sulfidation epithermal deposits. So the gold is transported as these complexes, golden chloride and golden sulfides. And once, well, we have an intrusion that releases the fluids. The fluids, as we said, they are strongly acidic, and so they basically flux through the country rock and end up leaching out the mobile elements, potassium and sodium. They leach out feldspars, as that's the case in the image there, and they just leave basically quartz or silica. And they leave a system that is porous and permeable, so later fluids transporting gold in complexes, they can basically migrate through this country rock and deposit the gold that we are interested in. And the deposition usually occurs either by mixing with shallow fluids or by mixing and boiling. So for instance, if we are transporting gold as a NHS complex, we reduce the temperature, we boil off some volatile elements or components from the brines, from the liquids. That releases these hydrogen sulfide gases, which reduces the solubility of gold and basically precipitates gold into pore spaces. And the processes are not too unlike what happens in low-sulfidation systems. Again, gold is transported as a disulfide complex. And again, this boiling causes the loss of H2S as vapor, which again stabilizes the gold and precipitates the gold. And it's a famous case where in the geothermal power plants in the Tapo volcanic zone, basically they are removing hot fluids from the crust, which carries gold. When we have the boiling in the system, we have precipitation of gold within the pipes. So every few years, the plant people they have to remove and clean out the piping where the boiling occurs. So the Tapo volcanic zone, as we mentioned, is where such systems are forming as we speak. And these dots are all geothermal systems due to basically injection of magmas from the subduction zone. We have this formation of many volcanoes and the geothermal field, geothermal systems, which are basically modern day epithermal deposits. We just have to maybe wait another few hundreds of thousands of years or million years to come back and know where to look for. What we know, however, is that in the Coromandel was Miocene volcanic arc. And there we have, like the Martin Line at Waihi and other systems, including porphyry systems here, which is, however, not easy to exploit because of environmental regulation and other things. And as I mentioned, porphyry system in New Zealand, they do occur, as you can see from this report from the GNS Science, or also from a master thesis of a Auckland University student. So to summarize, magmas start in the mantle, they contain dissolved volatiles. Lowering pressure and temperature as well as fractionating causes boiling and separation of these fluids which can then carry metals as complexes. And again, boiling of these fluids causes separation of metals, which are then precipitated as or minerals, and for deposits such as porphyry and GREISENs that are proximal to the intrusions, SKARN deposits, which are formed by reaction of carbonates, and epithermal deposits, which are the shallow end of the system. And next lecture, we'll be looking at more hydrothermal ore deposits, this time related to metamorphic or diagenetic processes.